Section 4.2, exponential functions. In this section of the notes, we're going to focus on solving exponential equations and compound interest and continuous interest equations. Example 4, solving an exponential equation. So we're going to have a few different forms of exponential equations to solve. The first thing that we should always check for is to see if we can solve this by rewriting this equation with common bases. In this case, we can, because we know that we can rewrite 1/3 as 3 to the negative 1 and 81 as 3 to the 4th power. If you're not sure why 1/3 equals 3 to the negative 1, then go back to the previous video and make sure that you've looked at those exponent properties that were reviewed at the very beginning. So we're going to start by writing our equation down and replacing 1/3 and 81 with 3 to the negative 1 and 3 to the 4th. Now I can simplify the negative 1 and the x by multiplying them together and getting negative x. Again, that's an exponent property that we reviewed. And now I'm going to set my exponents equal. So as soon as my bases are the same, both my bases are 3, I know that my exponents are going to have to be equal. So in the end, we get our answer of x equals negative 4. We could check this by plugging into our calculator 1/3 to the negative 4th power. Don't forget parentheses around the 1/3. And we would get out 81. Example 5, we're going to again start by looking at our bases, which are 2 and 8, and seeing if we can rewrite them as a common base. We know that 8 is the same thing as 2 to the 3rd power, so we can rewrite these as common bases. So start by replacing 8 with 2 to the 3rd power. Make sure that 2 to the 3rd is in parentheses here. And now, again, exponent rules tells me that I can multiply 3 and x minus 6. I'm going to do that by distributing. And now I can set my exponents equal and solve. In the end, we get x equals 11. We could check that by plugging it back into our original equation and making sure that we get a true statement. Example 6. We're going to solve the equation x to the 4/3 equals 81. Note that on this problem, we can't make common bases like we did on the last problems because x is one of our bases. So what we're going to do is we're going to rewrite x to the 4/3 in radical form and then use inverse operations to solve for x. So let's start by writing x in radical form. That's going to be the cube root of x to the 4th power. And now we're going to use inverse operations to move the 4 over and to move the 3 over. So 4 is an exponent. The inverse of power of 4, exponent of 4, would be a 4th root. So we're going to 4th root on both sides. Anytime we take an even root, we're going to always need to put a plus minus in front of our answer. Odd roots, we don't need to do that, only even roots. Next, we're going to get rid of the radical 3, the 3rd root, by taking to the power of 3 on both sides. So we get x equals plus minus 27. You can always check this by plugging it into your calculator, check 27, and then check a negative 27. Next, we're going to work on some interest problems, starting with compound interest. This formula here hopefully is familiar to you. Hopefully you've seen it before. So if P dollars are deposited in an account paying an annual interest rate of R, compounded, in times per year, then after T years, the account will contain A dollars according to this formula. So it might be helpful to kind of diagram this equation in your notes. A is the amount you have after the investment's over. P is your principal. I believe that my math lab calls that your previous amount. So it's how much you start by investing. R is your rate. Make sure you always take the decimal and turn it into a percent. Excuse me, I said that backwards. You're going to be given a percent. Make sure you turn it into a decimal. T is time, and N is number of times compounded in a year. So your problem might tell you that it compounds biannually, which would be 2. Might say quarterly, which would be 4. Monthly would be 12. Daily, 365. Example 7, using the compound interest formula. Suppose $1,000 is deposited in an account paying 4% interest per year, compounded quarterly. So here's what I just got from what I read. P is going to be 1,000, R is going to be 0.04, and N is going to be 4. Part A says find the amount in the account, so this would be finding A, after 10 years with no withdrawals. So we're finding A, and T is 10. We start off by plugging in each of those amounts for the variable that they go with. And then we're just going to simplify this equation. Depending on your calculator, you may just be able to type this whole thing in exactly like it looks and get out your answer. Some calculators that doesn't work so well, and I would advise you to plug in what's inside the parentheses first, see what you get, and then evaluate it from there. So in the end, we get 1,488.86, which is the amount that we have in the account after 10 years. Now, in these kind of problems, we're not going to tell you what you need to round to, because it should be understood that money is always rounded to 2 decimal places unless otherwise specified. Part B, how much interest is earned over the 10-year period? So same problem going on here. To find out how much interest we got, we're going to take the amount of money that was in the account after 10 years, so the 1,488.86, and subtract off the amount that we deposited. So we put $1,000 in this account, and after 10 years, it gained $488.86 in interest. Example 8, Part A. Becky Anderson must pay a lump sum of $6,000 in 5 years. What amount deposited today, so the present value, at 3.1% compounded annually will grow to $6,000 in 5 years? So she wants to have $6,000 5 years down the road. How much are we going to need to deposit? So we're solving for P here. So first of all, we know that A is 6,000. R is going to be 0.031. We just moved the decimal place to the left 2 spaces. N is 1 because the problem says compounds annually. And T is 5. We're going to start by simplifying inside of the parentheses and doing the 5 times 1 in the exponent. Then we divide both sides by that 1.031 to the 5th power, and we get our answer of $5,150.60. So that's how much money she has to invest now in order to have $6,000 in 5 years. Same problem here, but this time we're realizing that Becky only has $5,000 available to deposit now. What annual interest rate is necessary in order for her to get to $6,000 in 5 years? So this time it's asking us what interest rate we're going to be solving for R. So we know A is 6,000, P is 5,000, N is 1. So notice I don't have R over N because N is just 1. And T is going to be 5. We're going to start solving for r by dividing our p-value over. So in this case, it's 5,000. 6,000 divided by 5,000 is just going to be 6/5. Now we need to get rid of the exponent on the right side. The 1 is going to be dealt with at the end. So the exponent of 5, we're going to move it over by doing the inverse, which in this case would be the 5th root on both sides. So we get 6/5 to the 1/5 power equals 1 plus r. Remember, a 5th root is the same thing as the 1/5 power. Now I'm going to subtract over 1. And in my calculator, I'm going to put 6/5 to the 1/5 minus 1, and I get out 0.037. To make that into a percent, I'm going to move my decimal over twice, and I get 3.7%. So that is the rate that she needs in order to only have to invest $5,000 now and have $6,000 in 5 years. Continuous compounding. So in the problems that we just did, we were told how many times a year the interest compounded, whether it was quarterly or annually. Now we're going to talk about problems that continuously compound. So we have a new equation here. If P dollars are deposited at a rate of interest R compounded continuously for 10 years, the compounded amount A in dollars on deposit is given by the following formula. A equals P E to the RT. So I like to call this formula PERT for obvious reasons. P is still how much you are depositing in the beginning. A is how much money you have after the interest is compounded over however many years. R is still your rate, and T is time. E is a number. I have its approximate value down here, 2.718, so on and so forth. It's kind of like pi. It's an irrational number. Pi is 3.14, on and on. So E is going to be a button on your calculator. Take a minute and look at your calculator and see if you can find it. It might be Shift LN. That's what it is on my calculator. So you'll need to identify where yours is. Example 9. Suppose $5,000 is deposited in an account paying 3% interest compounded continuously for 5 years. So anytime a problem says compounded continuously, we're going to use this equation, PERT. Find the total amount, so find A, on deposit at the end of the year at the end of 5 years. So we're going to use our PERT function. We're plugging in 5,000 for P, 0.003 for our rate, and 5 for T. We can just plug that all in our calculator at once, and we get $5,809.17.